So this video is made for those of you who might have been absent or missed a little bit of notes that we took together in class on pages 5 and 6. And it's really just the bottom half of page 5 and then all of page 6 that we're going to be covering here. If you did miss the top half of page 5, that was the tail end of podcast 1.3. It started on page 3, did all of 3, 4, and then 5, that top half. So let's go ahead and finish out page 5. We're going to start by talking about pure substances, and you already have the definitions for elements and compounds. We'll talk about those more in a minute. But the definition that as chemistry teachers we agreed that you need to know for pure substances is a substance that cannot be separated or broken down by ordinary physical means. So that's what you need to write there by the words pure substances. And you do need to know that. But I think the most important part of that definition there, the thing that we should be keying in on when we think of a pure substance as a chemist, is the first two words, a substance, meaning just one substance. That's what we're talking about when we say something is pure. It's just that one thing in that bottle, in that cup, in that beaker, nothing else, no contamination. So, a pure substance is one substance, and yes, it can't be separated or broken down physically. But that's kind of secondary. Now, elements are a special type of pure substance. These are pure substances that, sure, can't be separated or broken down by physical means, but something we need to add here is that elements also can't be broken down by chemical means. Elements are the most basic unit of matter. They cannot be broken down until we make that stuff not matter anymore. We turn it into energy or something. So, elements can't be broken down physically or chemically. They are the basic building blocks of all matter, and they are the simplest little Legos in this kind of building world that we're talking about in chemistry. Now, I would like you to also add some examples of some elements. And if you've got some favorite elements, as long as you're sure they are elements, they are on that periodic table, feel free to just write down a couple of your own examples. That's fine. I chose some simple ones that you see a lot of: hydrogen, H, carbon, C, or aluminum, Al. And I did make sure to write those symbols there next to it to remind you that all of these elements, if something is an element, it has to be on our periodic table of elements, which means that it's going to have a symbol, a 1 or 2 letter symbol, in order to represent it. If you're thinking about something and wondering, is this an element? Ask yourself, is it on that periodic table? As things like air sometimes can seem like elements, and then some people call them elements in different circumstances, not chemists. But air isn't on the periodic table. It's not actually an element. So we can always find a single symbol for any element. Compounds, on the other hand, are 2 or more different elements that can combine chemically. And so because they've been combined chemically, they can only be separated chemically. So they can't be separated physically, but they can be separated chemically. And if we had some examples of those, some common examples of compounds are carbon dioxide. You can hear and see the 2 elements in there, carbon and oxygen, and CO2 there. And we'll learn how to write names and formulas, but here you can see that we can still write a formula for a compound. It has a definite ratio of those specific elements that have been combined chemically. And sometimes there's numbers along with them if there's more than one thing, but like sodium chloride. Sodium and chlorine bonded together into this NaCl thing, and that's just table salt. So salt is a compound. Sugar is a compound. It's a pure compound. Even though we have more than one element in there, every single molecule of salt and of sugar is exactly the same ratio of the same elements, and they've been combined chemically. So we can't just pick them apart from each other physically. You've got to do a chemical reaction to break it down and to make it separate again. So the opposite of a pure substance is a mixture. And so we see these 2 different types of mixtures down here that we're going to be getting into. But since mixtures really are just the opposite of pure substances, our definition here kind of keys into that. A mixture is a combination of 2 or more substances. And these 2 or more substances have been combined, just physically mixed together, not chemically combined. And so anything that's two or more substances in a mixture, most of the world around us are mixtures. And we technically have two different types of mixtures. Heterogeneous or heterogeneous mixtures are mixtures that are not smoothly blended throughout. That prefix hetero means different. So here I've got different stuff mixed together, sure, and I can still see that different stuff. It's not perfectly mixed. A homogeneous or homogeneous mixture, homo means same. So even though we've got different stuff in that mixture, it is mixed so well that we can't see the different stuff. Our definition here says that a mixture that has uniform composition, and just like if all of our students wore uniforms, then they would all look the same. And so that's what we're thinking about and keying in on with these different types of mixtures is, can I see the different stuff, or does that different stuff all look like it's one thing? I had a little note pop up here that I had forgotten about previously, that once we mix things together, because they're only physically combining, physically mixing, they're not changing chemically, which means that their chemical properties are going to be the same. So they're each going to retain their properties. Like I think of salt water. It still tastes like salt. That's a really simple property, but it didn't suddenly start tasting sweet when I mix the salt into the water. It's just combining together the properties of the salt and the water into this mixture. Now, I would like to write a couple of examples of these different types of mixtures, and in class I had people think of some examples, and then we classified them as either heterogeneous or homogeneous. And you can think of some other mixtures on your own, but make sure that they very clearly are homogeneous or heterogeneous. Some common examples that we had talked about were some food examples. So like pizza is definitely a heterogeneous mixture. If you don't like the olives that they put on the pizza, you can pick them off. You can see the separate bits. They're not smoothly blended, so you can pick them out if you don't like them. Things like salad were also pretty common examples. Sand is one that I like to bring up because even though the particles in sand are all generally about the same size, if you look at them, there's some dark ones, some light ones. They're not all perfectly mixed together. You can tell the different types of rocks and minerals that have gone into these sands, and you can still see those bits, so it's not homogeneous yet. Some examples of some homogeneous mixtures, though, are things like salt water. If we've mixed the salt in the water, stirred it up, it should all be dissolved, and you can't see that salt in the water separately, as long as you don't put way too much salt in it. They will mix perfectly. You can't see the separate stuff, so that's homogeneous. Brass. Metal is a mixture of metals, but you can't see the chunky separate metals. Air is also a mixture. We've got lots of different gases in the air, and there's not pockets of one gas compared to the other. They're all perfectly mixed. When you take a breath, you got plenty of oxygen there, you breathe out, that CO2 doesn't just stay there in a cloud around you. It mixes perfectly with all the other gases around you to give you a perfect homogeneous mixture every time. There's lots of other examples, and you'll see some in the next couple of pages of practice that you're going to do. But let's go ahead and move on to the next page where it asks us about alloys. So this might seem like kind of a random question, but it does have to do with these mixtures we were talking about. Alloys are just a special kind of mixture, specifically a kind that has a metal in it. It could be 2 metals or 3 metals or all metals, but we can also mix in other elements with it. So as long as it's a mixture that has a metal, it's primarily metal, I believe, then that is an alloy. And some examples, brass, like we talked about before, mixture of metals, copper and zinc specifically. They melt it together to make golden-looking doorknobs and keys and instruments. If you think you got a golden key on your keychain, it's probably not gold. There is not a single atom of gold in that key. It's just brass, copper, and zinc. Same with jewelry. Most jewelry is going to be an alloy, a mixture of a valuable, pretty metal with other metals. And it's not just so that they're cheaper, although that is one of the effects that it has, but it also helps make it stronger. If you had a pure gold, 24 karat gold ring, then it would get bent all the time and chipped and nicked, and it wouldn't look as pretty long term as you want it to, especially if it's a wedding ring wanting to represent your long-lasting marriage. Well, we want the ring to last as long as the marriage does. And alloys are used all over the place in the real world to combine these properties and make our metals better, stronger, lighter, in order to make them better for certain uses. So they're in rims and frames of vehicles, from cars, bikes, to airplanes and space shuttles. So alloys are very, very useful. Now, most of what we're doing here on this next page is filling in some questions to this flowchart. You've got those words that we were just talking about, but we need to fill in the questions that we should be asking, help kind of organize our brain as to how to take examples of matter and end up sorting them into these 4 main types of matter. So we're always going to start by asking ourselves the first main question that's going to help us tell the difference between our mixtures and our pure substances. And if you remember when we were talking about those on the previous page, what I said the best way to tell them apart was ask yourself, is it made of more than one substance? If it is, yes, then it's a mixture. If it's only one substance though, just one thing, it's pure. You might also make a note that those things that we are looking at, if they are physically combined, those more than one thing, then it's a mixture. Sometimes we have things like sodium chloride combining chemically, and that would be a pure compound. So one or more, or made of more than one thing that is physically combined makes us a mixture. And over on that mixture side of things, the question we need to be asking ourselves to tell whether something is a homogeneous or heterogeneous mixture is if it's all looking the same. So we want to see, or if it's all looking the same, same means homo. If it does not look the same, if we can see those different substances that we know are there and mixed together, but they're visible and separate, distinct groupings, then that would be heterogeneous. So, over on the pure substances side of things, our compounds are made of more than one element, so 2 or more different elements. Of course, they're chemically combined, but that doesn't matter as much. If you just have one element, not 2 or more, then it's an element. If you have 2 or more, it's a compound. So make sure you fill in those questions into that flowchart, and it's probably going to be helpful to use this flowchart and to practice going through and asking yourselves these questions in the right order on the next couple of pages when you're working on classifying substances, because it's not just about finding those answers and memorizing them. It's about knowing the right questions to ask to figure out and classify any substance, any mixture that we give you. So these are our different types of substances. What we're going to talk about down here underneath our flowchart is how to separate mixtures. We mentioned that these have been physically mixed together and they can be physically separated, but there are some mixtures that you might not really understand. How could you possibly separate these things? You can't just pick them apart with your fingers. So it might make you think that they're chemically combined, but there are some special techniques that chemists can use to separate mixtures. As long as they haven't been chemically combined, we can separate them out using some special techniques. So the 4 different techniques are already written there on your page. So as we go through each of these slides, you really just need to write down the details, the words that I've got here. Make sure that you can tell them apart and understand the difference between them and when you might want to use one over the other. So filtration specifically uses some kind of special paper, filter paper, to separate solids from liquids. And that last part is important. We cannot separate liquids from other liquids using filter paper. It's both just going to go through the paper. And we can't separate solids from other solids using filtration, because all of those solid pieces, no matter how big or small, are going to get caught in the filter paper. So filtration specifically is made to help separate solids from liquids, and we use a special paper. This is kind of a zoomed in view because there's holes between the particles of the paper, the actual kind of filaments that are put together into that paper. There's holes. And so the big holes are going to allow the smaller particles through. The liquid generally can squeeze and move through filter paper, but then the large particles get stuck, even in big holes. If they might be able to fit through one layer, then generally we have multiple layers, multiple kind of options or opportunities to filter out those big solid particles. So solids get stuck in the paper, liquids can travel through, and that's how we separate things that we otherwise couldn't. Like, think glitter water. There technically is a possibility that you could pick out every single piece of glitter from the water, but I'm willing to bet you'd miss one, and I probably wouldn't want to drink that water if you just used your hands to try and separate the glitter from the water. But if you filter it through filter paper, then you can be 100% certain that every single piece of glitter is getting caught, and as much of that water as possible is getting through the filter. And so I would feel comfortable drinking filtered glitter water as long as it went through some good filter paper. Decantation is where we pour a liquid off of a solid. So here we're still separating solids and liquids, but we're not using special paper. So usually this just kind of relies on the fact that our solids tend to be more dense and like to stay at the bottom of our cup or our beaker that we're pouring them out of, and our liquids are fluids, so they can move and flow. And so we can pour the liquid off the top of the solid without it rolling out. I always think of this as if you cook at all, you often have to open up some cans, and you probably have to decant some of the liquid off of the top of like black beans or something, so that you don't have all that liquidy stuff poured into your casserole or whatever you're making. So you can just kind of gently pour it, and the liquid will slowly pour off the top, and the beans will stay in decan as you decant the liquid. Now, distillation is a pretty fancy process, but it's a pretty simple idea that it's based off of. And we use distillation to separate two or more liquids based on their different boiling points. And they have to have even a slightly different boiling point for this to work. Because what happens, if we start with a mixture in this container of more than one liquid, then we heat up that container with both of the liquids in them so that it's between their boiling point, meaning above one of their boiling points and below the other's boiling point. And what that does is that the liquid that boils at that lower temperature is going to start boiling, but the one that boils at the higher temperature that we haven't reached yet will not boil. And so the boiling liquid will turn into a gas, and those vapors will go through a system of tubes where they're going to be allowed to cool back down. And then we can have our liquid again at the end, but it's now been separated because we force it to turn into a gas, so that as a gas we can separate it from the liquid, just because they like to flow and move and rise compared to our liquids. And so that's really all that distilling is using the fact that most liquids will have different boiling points. We heat them to right in between those boiling points, and we can boil one off while leaving the other one. The higher boiling one will still be left behind in that original flask. So we'll be able to get our two different liquids in two different flasks. And finally, chromatography. And chromatography is, like the prefix chroma implies, separating molecules based on the difference of attraction of these colored particles. Chromatography does generally need to be some kind of color-based separation, but the colors aren't why the separation is happening. It's more of the fact that because they're different colors, the molecules are different shapes and sizes. So really, the shapes and size difference is causing the different colors that we're seeing. And because these particles are different shapes and sizes, when we put a dot of this substance, this mixture, on a piece of paper and dip it into some kind of solvent, something that will dissolve the substances in that pigment, as the water level rises up, or as the solvent level rises, it's going to dissolve the pigment. But if this is a mixture of pigments, of different molecules, then some of those molecules are going to be better dissolved, better carried by our solvent liquid than others. So here you can see the lighter colored ones seem to be going farther. So the lighter colored ones are almost lighter, easier for the liquid to carry, so they're getting carried farther. The darker ones are heavier, so they seem to be getting dropped a little bit sooner. And the longer we leave that in our liquid, then the more of that separation that we're going to see. We definitely have more of the lighter stuff going farther and the darker stuff staying behind. So this is a color-based separation, but it's really a little more complicated chemistry kind of going on behind the scenes. But it is a way that we can separate mixtures, kind of by differences in which ones will dissolve or not, and the differences in their solubility there. So these are our methods of separating mixtures, which is where our notes are done. But if you haven't already taken the time to get started on worksheet 1A, which is the next 2 pages, then that is what we did next in class. And it goes all the way from physical, chemical stuff that was in that podcast 1.3 I talked about earlier, all the way through to this element compound mixture, classifying things with that flow chart, finding element names on the periodic table or from our element list, and, just listing the indicators of chemical changes. So all good stuff, all stuff you're going to need to be able to do by the time we get to our test. So if you haven't already tried these out, go ahead and give them a start. Let me know if you need help checking your answers. I have given you a few hints on Canvas. If you go into our modules and scroll down just a little bit, then these notes were posted right here, and right underneath it we have the pages 7 and 8 individual practice, and that is where I have posted some hints and tips. It's not necessarily the answers, but like in question number 1, if you have 3 physical and 3 chemical changes, you probably did it right. If you have 4 and 2, then you probably have 2 of them swapped, and if you can't figure out which ones, come in and ask for help. I haven't given you all of your answers, all of your hints, but sometimes I've just pointed you to the right place to go looking. If you don't know what these indicators of our chemical changes are, they should be written on page 14, or page 4, sorry. Or if you didn't even write them there, go back and click through podcast 1.3 until you see a list of those indicators that you need here. So hopefully this helps fill in those blanks. Let me know if you need help with any of this content or figuring out how this relates to what we're going to be seeing and doing in the future.